So I do want to get some feedback on what you guys thought of the assignment and the discussion session. I'm gonna postpone that until Wednesday's class. So I think on Wednesday we're gonna start with a little bit of a recap of what you guys thought of the assignment, how you use like AI, for example, if you did, what your experience was, what the pitfalls were, because some of you already identified that it's not actually so useful as you might think it is. It is, but it's a double-edged sword for sure. What I wanted to talk about today was introduce to you guys the idea of iterative solvers. There are a few. There's Jacobi, Gauss-Seidel, and successive over-relaxation. I want to talk about the pros and cons of each of the methods, and also I want to show you guys firsthand the benefit of all these things. This is kind of another thing. So I did conversation with one person in the lab. They mentioned like kind of the keywords that showed me where they've been reading up and the techniques they've been reading up. This is not that. Again, right? We kind of keep talking about like the background stuff, and then I tell you that, you know, this isn't actually the way that people do things nowadays. This isn't actually the way that people do things nowadays, but it's so fundamental that it's kind of baked into everything else. So the same thing with Gauss elimination. Nobody does that, but the way that it separates the L and the U matrix, and then you use that decomposition, that is there. And kind of like the bigger methods and stuff that people are using it, it's also in there. So it's kind of like one of these bedrock things, but I thought it was also kind of cool, actually, the concept behind it. Okay, so Gauss elimination, LU decomposition, and the such are direct solvers in that you can arrive at a solution in a fixed number of steps, right? Because all you're doing is you're taking the matrix, you're subtracting this, you have an answer. And in infinite precision, that would be the answer, the correct answer. Iterative solvers are different. Oh, sorry. So the problem with the direct solvers is that those number of steps, remember that we measure complexity in terms of the number of operations. Time-it is a good approximation, but it is just that. It's an approximation. Really what you want to be doing is counting the number of operations that you're taking. That's how you can normalize across all the different systems. Okay. Direct solvers typically scale around n cubed. So when you have like the really small solvers, a few people did identify that when you get the small solvers, the dense is actually faster than the sparse because the sparse has a little bit of overhead. But as soon as you get into the bigger and bigger systems, well, we'll see. We'll see what happens. Spoiler alert, sparse takes over. Iterative takes over. Sparse took over previously. Okay, so the idea with iterative is that we're going to start with an initial guess and iterate hopefully towards the solution. Hopefully is the key word in that sentence. Each iteration is typically faster and more memory efficient than direct solvers, but convergence is only guaranteed for certain types of matrices. And even then, the rate of convergence might be asymptotic. So you might, even though you will get to the solution, you might like take infinite time. It might be a thermodynamic thing, but time before you actually get there, right? And there are problems with that, but there are mitigation strategies. Other good things about them is that they're self-correcting. So if there is round, so whenever you have like an iterative technique, you kind of have to be thinking about round off error again, right? And like what happens when you do get a little bit of round off error? Is it a positive feedback situation where the error takes off, your entire method fails, or is it negative and it stabilizes again? We're getting into stabilization. Like this is the entire heart of time stepping later on, is all about stabilization. They are more conducive to sparse matrix storage, the iterative techniques, and that's just because of the way that they're structured. They don't tend to use the matrix expression so much. They kind of go through more summations. Now, matrix internally, I would assume is summation based anyway, but in general, the literature says this is how they're done. I see already a question, but I'm telling you what the textbooks are telling me. Yeah. Okay. Well, there we go. There we go. So another key point is that in each iteration, only the guess is being altered. So AX is equal to B, only X is being altered, which means whatever we do with A or B is permanent. You do that once at the beginning of your iterative loop and you don't touch it anymore. So you can pre-compile things. I forget what the computer science term is, lifting it. You lift it outside of the inner loop and it means you have computational gain. So you can optimize these things, which is nice. That's also where the sparse matrix comes in, because then you can negate certain terms based on how they actually appear with the or disappear through the zero pattern. But that's outside. That's optimization problem. Okay. In fact, there is a class of iterative solvers called matrix-free methods that avoid writing out A entirely, which is kind of interesting that you can solve a linear system without writing the linear system. But basically, the idea behind that one, also not in this one. I want to do like a graduate level linear system solver, or numerical methods course, and like this is where that would go in. But the whole idea is, instead of calculating AX, if you can approximate what that product AX would be, then you can actually avoid ever calculating A in the first place. But that's off there. Just to put that in your mind. So if you're looking up on this, if you're like doing online research, a few people mentioned singular value decomposition when they were talking about condition numbers, because if you Google it, that's what you're going to find, right? We don't need to talk about singular value decomposition, but I just want to like mention these words. So if you see them when you're Googling around, then you'll have some point of connection with what we're talking about here. Okay. Each iteration will improve the answer, hopefully, if it is a convergent series. But again, like we need to say, okay, this is good enough. And whenever we need to do something like that, we need to use tolerances, right? We're back to series expansions. We're back to order and notation. The approximation is good enough. Let's move on with our lives. So we're going to have to be defining this. Tomorrow, Wednesday. Nope. 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 Actually, gradient descent is not the right answer either. But that's Wednesday. Now you're really getting ahead of it. So let's talk about what it means for a vector x to satisfy ax is equal to b. Right? The top level for that is it's a vector. It satisfies a vector equation. Great. If you think about that a little bit more, what it's saying is, well, let me rephrase the question. I'm just gonna scroll out of that one. Okay. If I had XYZ, so my X vector is XYZ, never mind the double nomenclature, right? And I lost one of those. Say I lost Y. What would I do? Cry. After crying, think back to substitution. What happens when you have X and Z? You still need to find Y. How do you calculate Y? Tables and chairs. We found T. How do we find C? You just plug it into the equation, right? Yeah. So the idea is that each element in that vector, or the correct vector, is consistent in that they all satisfy that equation together. So if you were missing one of the terms, right, it's just substitution, right? You just go back and you substitute it, right? You make it consistent with the other information you have. So same situation, now you have one element that's a little bit wrong, right? You can use the other elements to push it in the right direction. And this is what the iterative scheme does. If one element isn't consistent, then we solve for it based on the other elements. This is why kind of we get away from the matrix notation. We actually circle back to it, but a modified matrix. This is why kind of like the looping and the index notation is a little bit cleaner, but there are a few different ways to visualize this. Shoot. Yes. Yeah. Ooh, 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 ooh. Them's fighting words. Okay. Put a pin in that one. So, big picture algorithm. We start with a guess. For every step, we identify a single element in X, make it consistent with all the other ones, and then we move on to the next one. And we just kind of go round robin And lo and behold, the thing actually solves, usually. Right? For certain conditions, we'll talk about what those conditions are. We are not going to derive why those conditions work. That's beyond engineering. That's like pure math. Yeah. We might also tune a parameter in there. That's a guessing parameter, or not a guessing, a weighting parameter. Okay. The system has converged when AX is equal to B. Therefore, do you guys remember like fitting data or something in like first year lab? You would do like Excel fit or something for your data, right? And you would get the residual, right? We're going to use the exact same idea for the residual. The residual is just AX minus B. When R is equal to 0, then it has converged. We don't want to check, right? What does that mean for a vector to equal 0? We could say that the vector, all the elements in the vector are 0, in which case R is the vector norm. We don't generally want to do that because different elements in that matrix will have different sensitivities. Instead, what we can do is use the norm of the vector, right? So again, this is the size. How big is the size of the vector? Is it massive? Is it small? Can we scale it accordingly? And then the question is, so we take the norm or some measure of magnitude of R, and then we say that it has converged when it decreases past a certain tolerance. Which tolerance? Do you want to use the absolute tolerance or the relative tolerance? Open question. Why? Okay, the relative tolerance between two successive solves, right? Yeah, okay. Anybody else? Yeah. So there is no right answer to that one. That one's a trick answer. There's actually another tolerance that you can also use, which is the next question. In general, the problem with that one is that if you're having a slow time converging, then the difference between successive iterations will be small, even though your residual is actually far off. So we would call this the method has stagnated. The problem with the absolute one is you could take your system of equations and just multiply through by 1,000 or any constant, and your residual would scale accordingly, right? In which case, what does absolute tolerance actually mean? Because you kind of got this arbitrary constant out front. So then you go into like scaling and you have to normalize things. This is all about the condition number 2. Surprise, surprise. In practice, generally what you would do is you would have both of them. You would have an absolute tolerance, you would have a relative tolerance, and you pretty quickly, like, honestly, with like moderate tolerances, it's just kind of rule of thumb, you get pretty decent convergence, or you know where to tune it. What other kind of tolerance could we look at? So here we're talking about the residual, and when the residual is 0, then you have solved the linear system. Are you solving for the residual? What's the quantity of interest in these iterative techniques? So, is there a tolerance that we can do on X? Let me give you an example. I have a function and I'm doing iterations. And my first guess is 4. Yeah, my guess for X to solve that problem is 4. My next guess is 2. My next guess is 1, 0.8, 0.7, 0.65, 0.656, 0.6563, right? Like, have I converged? Does that sound like my answer has converged? Right? So in that case, what you're doing is you're looking at the solution vector. And you can define, for example, you could say, what is my current solution versus my old solution? And you measure that difference. You do the norm of that. And now some people will call this the solution tolerance. And the idea there is that when your solution has stopped changing too much, then you've also reached your answer. The problem is that just like with relative tolerance for the residual, that's not actually the answer. Hopefully it's the answer, but you might have just stagnated. You might have just hit the bottom there. It depends on the conditioning number of your matrix. If your condition number is 1 or close to, which is the ideal conditioning number, hey everybody, right? Then all of your elements of your vector, of your unknown vector, are roughly in proportion. If it's wild, if it's like 10,000, then one of those is going to be much more sensitive than the other ones, which means that the solution you're going to get, first of all, you're going to have a hard time finding it because you're in some kind of a big valley or something like that. But otherwise, you can trust that value, but not any of the other ones, because the other ones are going to have too much slop. Your answer, your residual, isn't going to be very sensitive to those other ones. This kind of goes into the idea of scaling that we're going to have to get into later, scaling the input vectors. Okay. That's more with nonlinear solves that we'll be talking about scaling. Okay, Jacobi. Jacobi iteration method. Oops. My microphone's still on? Yeah. Begin by writing out. So what we have to do is we have to convert our matrix system into index notation, and then we actually end up bringing it back to matrix notation. I apologize, but this kind of way made sense to me. I wanted to give you guys both ways, depending on your way of thinking about it. Okay, AX is equal to B means that if you do index notation, show of hands, how many of you guys like would recognize the subscript IJ? Like it's kind of self-explanatory. It's literally the index of this 2D array. This matrix equation is equivalent to the summation here. So this is literally row. So this equation is saying for row I, sum every single element against every single element in X. And that equals to BI. Right? This is how we would do matrix multiplication by hand. This is kind of the fully expanded version where you can really see, okay, I'm just going row by column, row by column, row by column. What you do is you extract the ith row. So you're only looking at one row, and you solve for the diagonal term. So for the second row, what you would do is you would solve for A22. And when you do that, you express it in terms of the other elements in that vector. And this is the equation that you end up with. So you pull out of this sum, you pull out j is equal to I. That's your diagonal term. And everything else, so this is now the sum for j not I. Move that over to the side, and you solve for it. This is your new guess for xi. So we're demarking the iterations by the superscript. So beginning at xk, we calculate xik plus 1, the next version of that. So the idea is at every step, you're making xik plus 1 consistent with all the other elements of that vector. No, it's not an exponent, it's your iteration. So because we're going to be doing like every iteration is another increment in. So you're going to start off with like x0. Then you're going to calculate x1, which is your next guess. x2, x3, blah, 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 x1000. And hopefully by x1000, you've actually converged to a solution in some measure. Yeah? We can write this in a matrix form, but what we have to do is not LU decomposition. What we're going to do is we're going to rip apart the matrix A. And I'm sorry for the nomenclature. This is what all the books use, right? You just have to keep this in mind. This is not LU decomposition. What you do is you take your matrix and you literally rip out the lower triangle, the diagonal, and the upper triangle. Note that normally LU decomposition has the elements, the diagonal elements. In this case, those are 0 because you've literally just ripped this apart. Right? Wherever there's a blank here, I'm just assuming 0. This is my way of not having an entire page full of zeros. Okay? When you do that, and now I'll leave you just to stare at this for a while, because I just kind of had to stare at this until it made sense. This is the equation that you get. So this is the matrix equation, which will give you your new guess for x. So x1 based on x0, x2 based on x1, blah, 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 blah. Whenever you see any kind of matrix being inverted, you have to be careful because, as we spoke about last week, this completely destroys the sparsity patterns, and you need sparsity. You really, really want it. The exception being diagonal, because the inverse of a diagonal is also a diagonal. It's trivial to calculate. Okay, something to note about this. The next iteration, the next guess for x, relies on the entirety of xk. What that means is that you need to store two vectors. You need to store xk, your previous guess, and calculate and store xk plus 1. You have these two vectors you go back and forth on, and you change everything. That is more memory intensive than the alternative. Next one, Gauss-Seidel, but it parallelizes better because I can give a chunk of that vector to you, and a chunk of it to you, and a chunk of it to you. You can all iterate on those chunks and then bring it together afterwards. Okay? This is my little AI generated Jacobi step. So what I'm going to do here is I'm going to define these functions that take a single step. And then I'm going to put it together later on and show you guys the actual comparison. You can read through this if you want. It's, yes, let me guess, too many runtimes? Oh, wow, it ran. Okay, this is literally just the implementation of the example that I had above. Okay, whenever you write a test, whenever you write a function, it's a good idea just to test it on a super stupid example, just to see if the damn thing actually runs and gives you hopefully, and that's the first criteria. Second criteria gives you even a remotely good answer, a remotely useful answer. So this is the toy problem. We run it, and the first guess is 0, 0. Yes, 0, 0 is actually a good initial guess for your x vector. And there's a neat property with these things. In fact, they don't actually depend on the initial guess. If it's going to converge, it's going to converge no matter what, which is interesting. So with the guess at 0, 0, the residual norm is 7.8. Is that good? Is that bad? Doesn't really mean anything. You do one iteration, you get 1.25 and 2.0, and your residual has decreased. We can also solve it just for point of comparison. This is the actual solution. So we've seen the residual does decrease, good, and the solution moves in the right direction. Okay? So we trust this subfunction now. Gauss-Seidel, exactly the same idea, except you are now going to use, you're only going to keep track of one x vector. And every time you iterate it, that becomes your new basis. So you only have one vector, and xk plus 1, your new element, is made consistent with all of your other elements, including the ones that you've already updated. So it's a continuous thing. It accelerates things. It actually makes it more stable too, which is interesting. It's now stable for an additional type of matrix called Gauss-Seidel. You can write it in the matrix form. The matrix form is not as clean for me. That is a bit confusing for me at this point. I prefer the index form, but they're both there for you to take a look at. The benefit to this, you only need to store one x vector, because at every iteration, or at every step, every row, you're going to use the previous steps that you've already computed. So if you're going downwards, right, as you go down to the next one, you update that version and you recalculate. And then you go to the next one and now you have 2 updated. And you go to the next one, now you have 3 updated. So if you modify that vector in place, you only need 1. Half the memory requirement. Good. Distribution, bad. Because now you need to communicate that update to all of your other nodes. So it's a lot harder to communicate. It's a lot harder to do overhead. We're not going to get into distribution and parallelization at all because that's a black art, to be honest. Okay. What that does mean, though, is that its implementation is simpler because you don't need to worry about iteration numbers at that point. You're constantly doing one vector. But I say that, but at the same time, eventually you do need some kind of criteria to say that you have actually finished. So you might need to keep track of that, at least pedagogically. That depends on your implementation and the type of check that you're doing. I'm running out of time, so I'm going to speed up a bit. This is the implementation. Trust me. Don't trust me. Check it. But when I do the test, test number 1, it works. Good. Test number 2, it gives me an answer with a smaller residual and a guess that is closer to the real solution. And if you compare, this is 1.25, 1.58, 1.583 compared to this result, right? This is 1.25. The first one is the same because it's a 0 in the previous one. 2 becomes 1.58, which is closer. And the norm is also lower with Gauss-Seidel than Jacobi. We're going to see much more dramatic examples of this. Okay, successive over-relaxation. Gauss-Seidel can be slow. That's the problem. It can stagnate, and all of a sudden your convergence rate just kind of dies. So what you do is you can relax it. What that means is that whatever your increment in your next guess between xi new and xi old, we're going to multiply that by some scalar value. It's called a relaxation constant. It's given the term omega, or the constant omega. For omega is equal to 1, the method is exactly Gauss-Seidel, right? 1 minus omega is, when omega is 1, is 0, right? So all you're doing is just xk plus 1 is equal to blah, 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 Gauss-Seidel. When x is less than 1, you have damped the system. If you guys have talked about harmonic systems, right? You've damped it. You've taken a smaller step than the system would normally do. Is that more stable? Not necessarily. It just means it's not converging or diverging as fast. The opposite is you over-relax, hence successive over-relaxation. You multiply that by something more than 1. Typically, the guideline is somewhere between 1 and 2. And what you can do is you can converge to your answer faster. You might have noticed all my qualifiers. You can converge. You might get there. The real trick with over-relaxation is what the heck is omega? And there is no good answer. Unfortunately, there are different techniques that people can use. There's an example. This is from the textbook, Numerical Methods in Python. They give this way that you can determine. So let me back up for a second. Successive over-relaxation will outperform Gauss-Seidel for a well-chosen omega. But how do you find that omega before you calculate it, not after you calculate it? Because hindsight doesn't actually help you any. So there is a way that you can predict it. I didn't bother implementing this because this is outside of what I wanted to show you guys today. But there are various ways. If you look into the literature, you will see different techniques for how you choose this omega. SOR you are going to see in the wild. This is one of those standard toolboxes, just like LU decomposition. LU solve is going to be out there. You're going to be seeing that for the rest of your numerical life. You're going to see SOR. It won't necessarily be the workhorse, but it's going to be floating around. Just remember that for SOR, for omega is 1, it is Gauss-Seidel. Here is my AI generated. Here's my prompt, by the way. So I wrote the prompt. I wanted to show you guys like what it does. These are after my tweaks. I didn't show you my tweaks, right? But I want to show you guys like how you guys can do this sort of thing too. You just have to be able to understand, hint, hint, understand what AI is telling you and be able to like tweak it in the right place. Feel free to verify the math. I did. It's right. Well, as right as I can be compared to AI. Both of us are artificially intelligent. Testing it again, rerunning it. And we see it actually gives the exact same answer as Gauss-Seidel, even though I set my omega equal to, what did I say, 1.05 here. The reason is that my initial guess is 0, 0. So no matter what I put for omega, it's going to be multiplying it by 0. So that's why it doesn't show up in my little toy test, but you will see it change when I show you the actual things. So all of them are suitable for large sparse matrices. I covered that the matrix doesn't actually change iteration to iteration. They are generally more memory efficient and faster, but convergence isn't guaranteed. And even when it is guaranteed, then it can be slow. For some reason, the textbook says that iterative methods are slower. I think that is true for small matrix sizes. We'll see. We'll see it. Give you guys a live demo. Jacobi parallelizes well, but it's slower to converge. Convergence is guaranteed if A is diagonally dominant. And you might have started to think about that because you notice that the diagonal terms have special meaning, right? They are the inverse of those diagonal terms are the weights for making it consistent with everything else. So you might, like, diagonal is definitely important there, which means that you want to permute the rows potentially beforehand, and the big implementations will all do that automatically. That's why you get PLU decomposition. If your matrix is diagonally dominant, you're good. For Gauss-Seidel, faster convergence, actually you'll see much faster, but it doesn't parallelize as well. It is guaranteed to converge if A is diagonally dominant or symmetric positive, not positive. Positive definite, right? So if you remember symmetric positive definite, you can imagine as a quadratic, right? You're in the basin of a quadratic, and guess what's at the root? It's 0. That's where you're heading. Surprise, surprise, we'll see that. Okay, over relaxation reduces to Gauss-Seidel for omega 1. It may converge faster, it may diverge faster. Who knows? It may even if it is guaranteed to converge, it won't necessarily do that faster than omega is equal to 1. It really is a black art. The success hinges on, I shouldn't say that. The success hinges on the choice of omega. It's not a black art. It has to do with topics that are more advanced for this class. So what you have to do is look at the spectrum of the matrix. You need to do a partial eigen decomposition, and then you can tell about how much of a step you actually need to take. But for this level, you just kind of like take your chance, to be honest. It shares the guaranteed convergence for Gauss-Seidel as long as omega is between 0 and 2. And this is one of these proofs by the hardcore mathematicians that show this. Okay. So all of these, so here's my attempt to communicate to you guys how to think about this computationally. All of these methods feature a step, right? An iteration. And within that iteration, you can do a Jacobi step, you could do a Gauss-Seidel, or you could do an SOR. So let's make a framework for this program that we're going to run that's going to take as an argument one of these stepping functions: Jacobi step, Gaussian step, SOR step. Hence, that's why I defined them previously. First step first. So what we're going to do is we're going to start with a guess, the A matrix and the B vector. We're going to do something to guess the new guess. We're going to check how well that changes, right? All these convergence criteria are all ubiquitous, doesn't matter on the system. And then repeat, maybe updating a parameter. We're not going to here. First step, whenever you do this sort of thing, have an exit condition, have a failsafe. It's way too easy to say while the tolerance is above while the error is above a tolerance, repeat, and you've just created an infinite loop, and now Google complains at you or your computer just dies because you're stuck in a loop. So whatever your implementation, do have some kind of check against the maximum iterations. Nobody wants to be stuck in a loop. Here's my tolerance. This is a residual. I just went with an absolute residual tolerance. That's all I need for this demo, right? It's the same A, the same B, and our X naught is 0. The answer, I'm going to give you the answer. These two functions here, what I'm going to do for the first one is show you what the linear system actually looks like. AX plus B for a 2D system is actually a plot. Let's see what the plot is, and then we can see what those different systems are using, what the iterations are doing. This is just another AI generated tool that scales the plot so we can actually see the things that we want to see, which are the initial guess and the root, the actual solution. So just when you're going through this, that's what all this fun stuff is. Here's my matplotlib, blah, 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 and then I plot it. Okay. It looks like this, by the way. This is the contour plot. So these contours are, for any coordinate here, I have an X value and a Y value. Plug that into AX minus B. That's my residual. This contour plot is the contour of the residual. If you can't imagine that, this looks like a parabola. This is a paraboloid, I guess. Not sure. It's a warp parabola. Okay. Funny Python tool I want to put in your mind is that you can actually pass a function as an argument. So all of these Jacobi step, Gauss-Seidel step, SOR step, when you look back at it, these are function definitions. But I'm actually going to define it. I'm actually going to pass it as an argument. So here's my main one. So here I am just setting, like saying which function to use for method. Right? This is a super like hacky way. There are much better ways to implement this. Right? For a range I in max iter, I want to calculate using method. Whatever method is, that's the method that gets applied. Calculate the residual, print out some statements. I'm going to update. So what I'm going to do is I'm going to plot a line from the current guess to the next guess so that we can trace the path as it goes towards this thing. Check the tolerance and then update and repeat. Great. Lots of different ways to do this. Okay. Jacobi step takes 12 iterations. By all means, like take this home and honestly just kick it and see what you get, because you'll see all kinds of different neat things. Okay, and we're running out low on time here, so I'm going to go faster here. So this is the Jacobi step. It takes 12 iterations, and you can see that it kind of jumps around. There's probably mathematical reasons for exactly what this path is tracing beyond. Don't need to know it. Just it's kind of neat to look at. What you can do is, no, what happened there? My super elegant commenting out arguments. Let's uncomment the Gauss-Seidel step, and lo and behold, it converges in 6 iterations, which is nice, right? And you can see that the path it takes is much more direct. It just kind of zing, right? But note that this is not the gradient. This is not the downward gradient, nor would you expect it to be because you're not using the gradient. You're using this other arcane mix. Okay, this took 6 iterations. Let's see my awesome, elegant comment and uncomment. Oops. If I put the comment at the beginning. SOR converges in 5 iterations. Hallelujah. Complete disclosure, I had to ask AI, I had to ask Copilot to give me a system where it actually converged faster with SOR and what the omega should be. Because in general, like it was too much to find a system that actually works. You have to resort to that next level stuff. Okay, I just wanted to show you guys what happens when the system is not diagonally dominant. And I'm running super low on time. So what you can do is you can just go back here. You know what? I'm going to start with not symmetric, first of all. So this is now 4, 2, 1, 3. Jacobi, you can kind of see, wanders around a lot more, but it's still diagonally dominant. Therefore, it still takes it, it still works. If we don't have that, let's say, what did I have before? 2, 2? Right? So now you can see the path is wandering a whole lot more. And actually, depending on where you start, you may or may not converge. But still, the Gauss-Seidel outperforms it, which is nice. Okay, let's push it. So this is me. Yeah, this is me just generalizing. So this is me creating a diagonally dominant matrix so that we know our methods will converge. I'm just putting all that setup and everything into a function for convenience. It's the way I should have done it in the first place. I was lazy. Oops. Okay. Now let's run it for n is equal to 4. And we get the LU. So we're using the time-it function as a proxy for to measure the complexity. But we're going to see what it looks like. We're not going to judge what the order actually is. You're just going to see where the threshold is. LU takes microseconds. Jacobi, Gauss-Seidel, SOR. SOR actually takes longer than Gauss-Seidel. This is what I was saying. It gets a bit funny. Okay, let's go to n is 100. LU is still very fast. what is that, half a millisecond. We get half a second. Here the Jacobi is, oh no, so look at this. Jacobi is 570 milliseconds. Gauss-Seidel is 8.25. So that's already you get to see like what the convergence rate is better. N is 1000. I got a minute left. So here I just cut off Jacobi because it was taking too long. Jacobi is slow. Go with Gauss-Seidel. I don't think I even bother with SOR now. Now we're up to 40 milliseconds versus 89 milliseconds. 3000. We've crossed over. So this is, again, this is the whole order n notation, right? LU scales n cubed. This is doing another one. I don't actually know which this is. It gets kind of complicated because now you're a bit more stochastic, depending on the type of function and things. It's less easy to gauge. Okay. And if we do something like n 5000, then it gets much clearer to be better. So as you go up in size, you're going to get better and better and better with the iterative. Please note, this is a terrible implementation of Gauss-Seidel. In NumPy, you don't want to do for loops. Bad. You do vectorized methods, vectorization, optimization, all that. So this threshold is going to be a whole lot lower. But you can see that the iteratives are just going to dominate, especially as you go faster. I'm out of time. So today we're actually going to get to package tools. Hooray! This is the industrial strength iterative solvers, part 1. Tomorrow we're going to be talking about preconditioning. For that, that's a whole separate rant, but that'll be a rant for tomorrow. The goal of today is to get you to understand what iterative solvers are actually doing. Right, it's not quite the same. Gauss-Seidel is kind of like modifying the vector element by element to make it consistent. Actually, kind of a different. It's kind of like a right-hand turn. There's a pun in there that maybe you'll get at the end of the lecture when you're watching this for the 5th time or something. Right, I'm laughing, and I want you to be able to know how to use both conjugate gradient and GMRES. Spoilers, conjugate gradient is going to be your go-to for symmetric positive definite matrices. And you would actually be surprised. So like almost all energy equations, right? Everybody loves energy, especially engineers. Engineers, energy, right? Not a coincidence. End up being symmetric positive definite, and CG is kind of your go-to for that for efficiency, speed, and guaranteed convergence, which is very nice. GMRES is everything else, effectively. So basically, out in the world, what you're going to be doing is, first off the bat, LU solver. LU takes too long, then you switch over. Chances are it's going to shuttle you off to GMRES. GMRES, I don't actually know if GMRES is a thing or if it's just me, like just slamming the word together. GMRES. GMRES is great. It's fantastic, but CG is usually considered better. Although actually in this case, we'll see that GMRES actually outperforms it. But there are probably other reasons for that one. Okay, I apologize in advance. I couldn't get the information out without, so let me back up a second. To this point, I've been very loose with my mathematics notation, right? Like matrices are capitals. Everything else is basically a vector. AX equals B, right? Capital A, that's a matrix. Lowercase x, is that supposed to be a vector or a scalar? That's kind of whatever I need it to be, right? I had to take that out for this because it's just needed to get into the details of what's happening. So the nomenclature that I established here was capital letters for matrices still. Vectors have arrows above them, and scalars are just lowercase. Subscripts are still the iteration number. But actually, I say that in like 2 paragraphs down, I have it as a power. So generally speaking, they're iteration numbers. Excuse me. Some of these equations are pretty messy. The alternative is to use, instead of the vector with the arrow on top, I can just boldface that as a vector, and that's also a commonly encountered thing. So if some of these equations get really messy and it's hard to follow along, I can just do a search and replace and change those all to boldface, just for studying purposes. Okay, conjugate gradient. Consider, so we have an equation AX is equal to B, right? I'm not writing that down for like the 15th time. Consider a quadratic surface defined by this equation, right? This is, I mean, it's standard, it's a quadratic, right? In this case, A, because it's a multivariate quadratic, you have to have a matrix in for your second derivative, but otherwise it looks exactly the same. I tend to omit transposes. By the way, I had to put them in here because you're going to see they're going to be flying all over the place. NumPy, for example, generally doesn't care about transpose. I don't know if you guys have noticed that, but oftentimes it cares more about the fact that it's a list and it performs its operations along axes. And sometimes it gets a bit messy, but like when you see an axes option in there, that's what it's talking about. Okay. The surface, this quadratic surface has a minimum at ax is equal to b, hooray, or ax minus b is equal to 0. Let's define our residual exactly like we did last time and now say that the residual is the 0 vector. Okay, therefore minimizing f is equivalent, f is a scalar, by the way, f is a scalar surface, is equivalent to solving ax is equal to b, or that the residual is equal to 0. For a general guess of x, it will not equal 0 because you have not reached that extremum, right? Yeah. As a quick aside, in this context, A takes the role of something called the Hessian. The Hessian is one of these vector calculus functions. That should be a capital here. It is the second derivative of a scalar function with respect to, so put out into this matrix, right? It's by the rule of mixed second derivatives, right? So like di-f by di-a, or di-f by di-x, sorry, di squared f by xy is equal to di squared f by yx, right? Because it's a single surface, it's a field, therefore it has to be continuous, and you have this mixed rule. Therefore, the Hessian is symmetric, right? We're working towards conjugate gradient. Okay. Let's see. The Hessian is positive definite if this funny equation, right? Essentially what this is saying is that it's a quadratic surface and it's open up. It's a convex surface, right? For a 1D case, this devolves into positive second derivative. Good, we've made the connection. For comparison, the other vector function that also deals with the second derivatives is the Laplacian. You guys probably, I assume you came across that with the multiphysics course, computational multiphysics, right? Yeah. Okay. So the Laplacian is actually the trace. You guys don't know what the trace is. The sum of the diagonal elements of the Hessian, right? So just don't get those two confused. Laplacian is a scalar. Hessian is a matrix, symmetric matrix. Okay. Since A is symmetric, you can make a surface F that has an extremum at the solution. The problem is that if it's symmetric positive definite, then it's an open convex. That extremum is a minimum. Fine. If it is not positive definite, you can still make a surface, but now it looks like a saddle. Like a horse saddle, in that it goes like this in one dimension, positive second derivative, and like this in the other direction. So you can imagine a saddle, and they're called saddle point problems, and they're notorious. They're tremendously difficult, but they pop up all over the place, especially in optimization. So there are different strategies that you can do to try and get this thing, but it's a lot harder. So all of that to justify what exactly we're doing here and to qualify these terms. Okay. The algorithm that we're going to be doing is we're going to start at our initial guess, xk. We're going to choose a direction to step in for our next guess, and then we're going to choose a step length. Two separate operations, right? And that's how we're going to reach our next step. Okay? So once we have a direction, so skip the first part for a second. Once we have a direction, how far should we step? Take a guess. How do we calculate how far we should step? Somebody give me a guess here. Remember, we've pictured this, right? We're on a quadratic surface. We're on a guess over here. And we know that we're going to be stepping in this direction. How far should we step? What's that? No, we're trying to get down to the bottom. We're trying to get to the bottom of this. Right. So we picked, so we don't know where the bottom is. We know the direction that we're going to go in. Right. But the question is how far along that direction we should go. Yes. Yes. Well, that's how you determine the direction. You're getting ahead of me there. So no, no, even better. Even better. Yeah. So now you're getting ahead with the gradient descent part, and that's more a question of optimization. In this particular case, you can just minimize it. That's the answer. So if you have your quadratic surface, you have your f, you know where your initial point is, you know the direction that you're going, and you can calculate just how far you need to go in order to reach the minimum in that direction. And it's this equation. Well, you have f. That's the thing, right? Because it's a linear system, you can construct your surface f, and you can do analytical calculus on it. Question. I'm excited. Yeah. I have my joke for thermodynamics. So in thermodynamics, factorials show up all over the place. Then you pronounce it like F bang. But anyway, okay. So the whole idea is that you pick your direction and then you're going to minimize your surface moving in that direction. You can calculate it, right? F of x plus alpha k. Remember, we fixed alpha k. You write out your equation. You do some churning and you get down to this line, which determines your step length. Do you guys want me to go through this math, or are you okay with trust me, guy, and you look at it later? Excellent. I'm not going to ask you to actually implement this. We're going to use the package tools. So to be honest, follow along the math if you really want, but the package is doing it right. Okay. Given a step direction, I hated in undergrad when like the prof goes off on like a proof, and like you're teaching it at a university, like people are relying on these tools for their everyday applications. It obviously works. Like I don't actually care why they, the proof for it. But anyway, so the whole point is, given x naught, given our search direction, we can optimize the step length in that direction. That being the one that minimizes R. It minimizes the quadratic surface, but it also minimizes the residual for that system. Good. Next question is, how do we choose a step direction? Right? And you guys, I think, both hit on it, which is gradient descent. Right? So the whole point is, or steepest descent, I should say, right? We can just say, we can calculate the gradient of f at that point and move in that direction. This is called the method of steepest descent. And the nice thing is that the gradient actually turns out to be the residual. So, hey, that's great. We're moving in the direction of the residual in order to minimize the norm of that residual. Makes sense. No problem. We put that in. We can calculate the optimal step length for that. And we just keep iterating until we've reached our tolerance. So again, we look at the norm of the residual. It falls below a tolerance. Fine, we're good. Okay. This is the copy and paste of the surface plotter that I put out last lecture. So we're taking that function and now we're looking at a quadratic. So I'm going to plot out those contours of it. And then AI spits out a nice steepest descent algorithm. Great success. Feel free to look into the algorithm. You can see how it works. But more importantly, is that it does work. There we go. So we're starting off at the origin because why not? And here's what happens when we follow the steepest descent. We go boom, 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 boom. 9 iterations. This is actually really bad. This is actually terrible. You don't want to do this. The problem is that you have this frenetic zigzag, right? Where you're going back and forth and back and forth. Let's see. Ba, 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 ba. So what this means, so we're going to do better. This is not conjugate gradient. This is steepest descent. What this means is that, so this took 9 iterations. X9 is equal to the first one, your initial guess, plus alpha 1, S1 direction, alpha 2, S2 direction, alpha 3, blah, 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 right? What does this expression remind you guys of? Is that? No, not Taylor series. Was that? Now Fourier series. It's not a series. I know I wrote expansion there. Correct. Which means it is a, what's that? It is a vector space. Yes. Did you read it? That is came down. No, you're exactly correct. It is a vector space. And more specifically, these S directions, these search directions, are the basis of your space, which makes sense, right? You're moving in that direction. What's your component for that direction? It's alpha, right? What's your component for that one? It's alpha 2, blah, 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 right? The problem is that we have 9 directions here. So this series goes up to 9, and each one has a component. Now, in a 2D surface, you could, like, we're used to writing X and Y, right? We could define one vector that goes like this. If we wanted to write out a vector in 2D space, we could define one vector that goes like this, another one that goes like this, another one that goes like this. There's nothing stopping us except for common sense. We don't want to do that. What we want to do is use orthogonal coordinates so that the step in one direction doesn't undo the step in another direction, and hopefully we won't need 9 steps, 9 basis vectors to describe a 2D surface. Doesn't make sense. So how do we ensure that the next step doesn't undo the previous steps? And this is where the conjugate gradient ends up. And also, this is also the basis of GMRES. So that's why I'm saying this, but there's a few key differences here. Okay. What we want to do is choose the next step to be in some sense orthogonal to the previous steps, plural, okay? In that way, they won't undo each other. They'll add to the solution. They won't just go back and forth and back and forth. What that means is that the next step kind of has to have information. So with steepest descent, every step direction has nothing to do with the previous steps. And this is the problem with it. So let's introduce it. And let's introduce it via this equation. This is from the textbook. Right? So we say this is the next step is proportional to the gradient, right? Steepest descent, R, plus this other constant times actually all the previous steps. But let's start off with 2D. Okay? And what we want to say is that these two vectors, k plus 1 and k, are conjugate to each other. Conjugate is not orthogonal. Conjugate is a little bit different, and hence the name. Okay? SK1 and SK are not orthogonal. The vectors SK1 and the matrix ASK are orthogonal. So what that means is that the next step is orthogonal to the action, one would call it, of the previous steps. And that's what actually makes it not overlap with every other step. But when we look at it, and we'll take a look at it, SK1 and SK are not going to be orthogonal. You do some basic math, you do the hokey pokey, you find your beta, it's this expression. Now you get a closed form expression. Great. And then again, you have your direction. So now you just optimize your step length. Exactly the same way, exactly the same result. Okay. we're actually going to be using all the previous steps. So every new step is going to be moving, for the most part, in the steepest descent, because you do want to reach a solution. But we're also requiring it to be orthogonal to all the previous steps, right? So this term actually becomes a sum. Let's do it. That's the true answer. Here are the, so this is the conjugate gradient method that's in SciPy. It's pretty easy. The only thing that I'm going to highlight in this case is the callback function. Feel free to look this up on, it's just Google it, SciPy, CG. What you do is you put in your matrices, A, your vector B, your initial guess, X, and then I add in this callback function. What the callback is doing is every time the conjugate gradient method takes a step, it's going to be calling this function. So that's how we can get out of this method what the iterations actually are, right? So up here, I'm defining, okay, iterations, I'm making a list, I'm saying this is equal to the initial guess, and then every iteration that it takes, every time this function is called, I'm going to be adding on whatever the current iteration is and chucking it into this function. And also printing it, by the way. Okay, so here's my list of iterations. And here's a result. Yay, right? So first of all, directions, not conjugate. Second of all, there's only two. Why? It's a 2D surface. How many linearly independent vectors do you need to map out a 2D surface? 2. Which means conjugate gradient, because it's always generating these linearly independent actions. I got to be careful here because the two directions are not linearly, well, they're linearly independent, but they're not orthogonal, hence the conjugacy, blah, blah, blah. Math, input math terms here. Yeah, the conjugate gradient necessarily converges in no more than n iterations. Right? So if your vector surface or if your unknown is 100, n is 100, it'll take at most 100. So some people actually consider conjugate gradient and actually GMRES also as direct methods because it's guaranteed to solve the problem within a fixed step. And it is the exact solution to assuming infinite precision. No, because every iteration has more. So just because you're taking n iterations, it depends on how many operations the inner iteration is doing. Yeah, usually, okay, let me finish this and then I'll come back to the question of complexity because it has bearing for tomorrow's thing too. Okay, so we saved the iteration list so we can look at what those directions actually are, right? This is the second row minus the first, third minus the second, we're indexed to 0. Here are the two directions that the method ended up choosing, right? The dot product is non-zero because those directions aren't orthogonal, but every direction is orthogonal to the action of your matrix on that. Okay, and vice versa, by the way, they're reversible. So S1 on AS2 and S2 on AS1. Okay. Another interesting property is that the residuals are actually orthogonal. And this time actually orthogonal, no conjugate, anything. What that means is that if you actually calculate what they are, when you do the dot product between the residuals, you end up getting 0. And that's pretty nice because now when you're doing the implementation of the algorithm, you don't need to calculate that. You know for a fact that it's 0. Also makes it more efficient. Okay. So, question about complexity. Generally speaking, maybe I should have mentioned this first since I'm going to mention it tomorrow. Generally speaking, iterative okay. Let me back up on that, back up. Yeah, okay. CG is guaranteed to converge, infinite precision, in at most n steps. Typically what happens is that the later steps, because you're following that gradient descent component, you end up taking like your largest steps at the beginning, and then they get smaller and smaller and smaller, as you would expect, right? Because your curve is doing something like this, right? So your largest gradient is going to be at the beginning, and then you take smaller and smaller and smaller. So CG usually converges to the tolerance way before n steps, which is good when you have a vector that's a million, right? A million degrees of freedom, elements in it, dimension. So with complexity, people don't usually talk about the complexity of iterative solvers, because you would almost never use iterative solvers without preconditioners in there too, which is tomorrow's lecture. And preconditioners just kind of like throw everything out the window, to be honest. Preconditioners are just kind of a black art to find like the right combination of preconditioners, and generating those preconditioners is kind of screwy. So generally at that point, people do actually look at the computational time and memory and stability. But now I'm getting into tomorrow's lecture. So let's see. In the analysis, so let's consider this, right? We're starting at x naught, we're moving towards x approximate, it's our approximation of the true answer through the expansion, blah, blah, blah. And this is, as you said, right? This is a vector basis. That's what we're doing. At the same time, we've also calculated what the optimal components are in those directions. Steepest descent doesn't enforce them all to be orthogonal or even conjugate. And that's what results in all this wasted time going back and forth. The conjugate gradient does enforce that so that they don't overlap. It only works because the matrix, because A is symmetric positive definite. If it's not SPD, this conjugacy doesn't work. And that's why you can only use conjugate gradient. Like that's serious mathematics as to why that's the case. But without that, it's not going to work. Okay. One other note is if you look at these equations for beta and alpha, you see that, where's alpha up here? You see that the only time that you see the matrix A is in combination with a vector sk, right? Here it is here. Similarly for beta over here. What that means is that we don't actually need to calculate A. We don't need to build it in the first place. We don't necessarily need to multiply vectors by A. We don't need to store it. That's nice. And that kind of leads into matrix free methods. So there are matrix free implementations of conjugate gradient and GMRES. They're very important for the really big systems, billions of elements in your unknown vector. We're not going to go into them because it's a bit too high, but you can see that because we never do anything to A other than multiply it by S, if we can just find another way to obtain AS, then we've simplified everything and we don't need to calculate that, which is good. To undo. Okay, the space of the solution is just its dimension. Conjugate gradient determines linearly independent vectors. So at most it needs n. Yeah, okay. So this is a 10 by 10. And here we go through it. We're generating the matrix. It's a random matrix. This funny thing here where we're doing the matrix multiplied by the transpose is the quickest and cheapest way to get a symmetric matrix. And because all of its elements are positive, then we're good and we can use CG. Here, this is a different callback routine that keeps track of both the iterations as well as the actual vector that it's doing, the iterate that it's doing. And when we go through, we get our solution. Notice that as we get closer and closer to the solution, these vectors change less and less and less. And that's why we can safely like terminate it early. In this particular case, this matrix is dense, so that's not so obvious. With sparse matrices, it converges in much less time compared to the matrix. So by example, a million by a million might take like 30 iterations to reach the tolerance, which is much better than a million. That's good. Okay. Ba ba ba. Sometimes, so here's a little bit of a fallacy. Because every step direction is being built on all the other ones, if there's any kind of error in the other ones, it's going to propagate. Not just that, but like if you do have a vector of dimension at a million, for example, right? That's going to be a million different search vectors. Gets to be a large memory storage requirement. So let's implement something called a restart. So when you look at some of these documentations for the SciPy conjugate gradient, I don't think you do have the option to do a restart, or at least not in the current implementations. For GMRES, you almost always have restart. So what restart does is after you've reached a certain number of direction vectors, then delete them all, start over again. Hopefully at that point, you're out of any kind of troublesome part and you're into a better defined region. Hopefully. Again, iterative techniques, bit of a black art. Any questions on CG? Not yet. Fair enough. Finally, we hit the big guy. Let's look at the case of A being a general non-symmetric matrix. Since it's non-symmetric, it is not a Hessian by definition, and therefore we cannot envision this. We should not envision this. We can imagine whatever we want, but we should not envision this as a scalar surface. Okay? However, we can do the same kind of treatment as we did with conjugate gradient. We take the residual of the system, still hasn't changed. We minimize its Euclidean norm, right? Throw back to the norms. We begin at our initial guess, x naught, and we're going to build a basis for that movement from x naught to our answer, x approximate. In the exact same way, except now we can't use that conjugacy. Now we're reduced to making things orthogonal. So every step in GMRES is moving in an orthogonal direction. Actually, usually the way that they're implemented, it turns into an orthonormal coordinate system, right? So then the magnitude is 1. In the previous one, the magnitude didn't have to be 1 because we're just optimizing the step length anyway. But see, GMRES just makes it simpler by doing that. And again, that leads down to simplifications later on. Okay. Since everyone is linearly independent, it will converge in at most n iterations, but typically converges a lot faster, and that's very useful. Again, the problem with that one is because we're doing the orthogonality of orthogonality of orthogonality, any kind of round off error is going to grow. So again, we implement the restart and frankly hope for the best. I don't think there is actually a good reason why, like because it's kind of stochastic with the random round off. There's no good reason why it should work, but here it is. No, sorry. There's good reason why it shouldn't work, but there's not a rigorous mathematical proof. I don't think. Okay. Bum, 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 bum. So the condition that the subsequent step directions are orthogonal is really the distinguishing factor. It also, in general, slows it down. But actually, when I do it here, well, first of all, for a two-dimensional case, obviously it's only going to take 2 iterations, right? It's too small to be to really have much of effect. But actually, even when I go for the larger one, it converges faster than conjugate gradient did, which in general it won't be the case, but for this particular one, it is. I was hoping to be able to extract the iterations like I did for conjugate gradient so that we could see the path that it's taking. Because the SciPy GMRES function, it's up here, by the way, because this function actually downgrades it into Fortran, it's actually running a Fortran algorithm underneath. Apparently, I am not able to extract the iterations. So if you guys are playing around with this in the assignment, hint, hint, and you're able to find out like the right combination of callback that actually spits out those iterations. Sorry, I should back up a second. If you look into the documentation for SciPy GMRES, and I encourage you to do that, you'll see buried down at the bottom, they've changed the versioning to say you need the callback type. Okay. It turns out that if you ask it to spit out the iterations or the iterates, the guesses at every point, it only actually does that every restart, not every time it calls it. I don't know why. This is a problem with using the package, right? Like when you're writing your own code / getting AI to write it, right? Like you can do whatever you want with it, but this is what happens when, especially you dump it down to Fortran. All the stuff is made in Fortran, by the way. Like I honestly, I don't know anybody who knows. Do you know how to use Fortran? Okay, I don't know anybody who knows Fortran. Anybody ever use Fortran? Yeah. Yeah. Did it work? Yeah. Yeah, yeah. It's one of those things I think I did at one point, but it was kind of like tweak this, and I tweaked it and then closed it and never looked at it again. So it's kind of funny, but like all of these algorithms and everything are usually implemented in Fortran because they're old because they worked. That's why people keep using them. So yeah, if anybody manages to get out like the actual iterations, please let me know and we can look at the path that it's taking. But in lieu of that, what I could do is find the residual at each step. I don't know why I could find the residual and not the iterations, but there it is. Fortran magic. One last thing you might see in GMRES when you're going to research it. Let's see what it. Okay, so there's the restart, tolerance. Oh yeah, two more things. Which tolerance do you use? So you're looking at the tolerance of the residual. I think I wrote that down, and I guess I didn't talk about it. So how do you tell when this method has converged? Somebody? Tolerance. Which tolerance? Any of them is the actual answer. Right? Yeah. Yeah. You can see I only have like a limited number of jokes, and then I just kind of recycle them. Absolute tolerance is a good one. Relative tolerance. These implementations don't have the solution tolerance. Other implementations, we're not going to get to PETSI, which is kind of like my personal go-to for actual like industrial strength linear solvers. I'm going to talk about PETSI more tomorrow, about the sort of thing it can do, but like that will give you the solution tolerance. The problem again with the solution tolerance and the relative tolerance is that we don't know that it's converged. All we know is that it's not converging fast. Right? That's a little bit of a problem. The other thing is with an orthogonal, so imagine you're in three-dimensional space and you start off with a step that goes like that. Which vector is orthogonal? Right? You have this whole swath all the way around. Yeah, right. So there are different. It looks like this particular implementation, it probably implements, what is it, the Gram-Schmidt orthogonalization. Again, something we're not going to have to talk about. It has the default way of determining that orthogonal vector. There are options where you can swap it out with another one. We don't need to worry about that one, but just put that on your radar that is an option, that is a parameter that comes up. It's to do with orthogonalization. Generally speaking, whatever the default is, just keep it. I've never had success swapping it. I have swapped it. I've seen the residuals behave differently, but I've just swapped it back because there's no actual payoff. Any questions? Okay. There's no questions, then we got 6 minutes of our lives back. No, I said you said no questions, man. So you do not have 5-6 minutes of your life back now. Sure. So the question there was somebody zoomed out or zoned out the first little while, so apparently I need to go back. No, that's fine. I'm just giving you a hard time. The idea is that if A is symmetric, then you can write, like normally you would have AX is equal to B. You integrate that over X. And so instead of a line, you get a quadratic. So if A is symmetric, you can say that there is a quadratic surface that has a minimum, that has an extremum at AX is equal to B. If A is symmetric positive definite, then that surface is a paraboloid, which is a generalization of basically a quadratic, and it is convex, meaning that that extremum is necessarily a single unique minimum. If it is not positive definite, but still symmetric, then you can have a weirdo saddle shape. Yeah. In which case it becomes harder, because you can imagine why that's harder to find, right? Because then when you're looking for the optimum step size, what's the minimum in that direction? Well, it's negative infinity, right? So that's why it gets different like that. Does that clarify things? Excellent. Anybody else? Anybody online? 3 minutes back. See you guys tomorrow. Thank you. So this lecture is going to be a little bit different than the other ones I've given. None of the textbooks have this. And to be frank, I was kind of shocked, because preconditioners, like all of modern computing, is all about preconditioners nowadays. This is the key to like modern HPC and modern solution for these things. And to be frank, like you guys are gonna come up on these things. Therefore, I wanted to at least expose you to it. On the other side, that means that like I don't have the usual resources that I have to help explain and like break down the equations and stuff like that. So all of this, I'm actually drawing from this link here. See if it actually works. Blah, 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 blah. Yeah. So feel free to have a look down here. You have to go all the way down here to, where was it? Preconditioning. Okay. And then I'll give you the examples that I literally copied and pasted from here entirely, to be entirely honest. Yeah, and there's a very good reason why I copied and pasted, and I assume that's the reason why they aren't in any of the textbooks. I'll come to that one. Okay, so what I want to do today is I want you guys to understand what a preconditioner is, right? I think we already know what a preconditioner is. What makes a good preconditioner? What makes a bad one? We want to be able to use the package implementations to solve certain linear systems. I'm qualifying there, very important one. And to recognize the big picture of why these things are so critical for HPC. Everybody here familiar with HPC? You know what the terminology is? Okay, I'll talk about it. Okay. The basic strategy of preconditioning is to modify the original linear system to something that behaves better, right? What does better mean? Turns out there are a bunch of things. Direct solvers don't need like user selected interventions for preconditioners, because something like we saw with the Gaussian elimination, the row ordering and the diagonal dominance is something that's like kind of so trivial and so robust that it just does it automatically. And that's why it spat out the PLU decomposition. That was the missing trick that I'm sure you guys all found. Yeah, iterative solvers benefit dramatically from preconditioners if you can find the right one. They're very good for efficient conversion, scalability, and for controlling roundoff. Almost all the implementations for sparse matrix solvers that you're going to find out there, especially at least the iterative ones, are going to expect a preconditioner, and they're going to expect a preconditioner of a certain form. So I'll show you guys what I mean by that. Unfortunately, there is no general preconditioning technique that always works well. And in my personal experience, almost all of the preconditioners fail miserably for every single thing, except for a single problem. And finding that like diamond in the rough is terrible. Just absolutely terrible. So I'm gonna run you guys through like the basic concepts, and then I have my Mike's tips at the bottom here, and I'll tell you what I've actually found to work. Good. Yeah. So certain preconditioners are designed for particular types of physics. This goes into the whole spectral analysis that you kind of touched on. Basically, the idea is that certain physics has certain eigenfunction characteristics. So you can imagine like elasticity is a good one. You do Fourier analysis, you can find out the wave speeds, blah, 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 blah. Right? It works like that. It's the same idea for the linear systems that come out when you try and solve those things. They have spectral properties. That's where the terminology comes from. The problem is that even if you have the right preconditioner for that type of physics, your boundary conditions can torpedo it. Right? If you have a heat transport equation and you have Dirichlet boundary conditions, so you set the temperature around the perimeter, that might solve using a preconditioner. But if instead you say that it's just insulation, and you have a time-dependent temperature, now you don't have that fixed boundary on the outside, and all of a sudden your nice, beautiful preconditioner just goes straight down the toilet. So, welcome to the crap here. That being said, they are the field of research right now. I'll show you why. Basically, anything larger than like a million. We've been using the terms elements, your dimensionality of your unknown. Typically, we would say DOFs, degrees of freedom. Anything more than a million DOFs, you're going to be looking at, first of all, sparse matrices. And as soon as you look at sparse matrices, you're almost categorically going to be looking at iterative techniques and therefore preconditioners. Also with HPC, I'll get there. We're not going to talk about the mathematics. Sorry. Of these things. I'm going to give you the general idea, skip over the math, and just show you the package implementations. Okay. Considering a linear system, AX equals B. You notice I dropped all the vector notation and all that fun stuff. Don't need it anymore. We want to multiply the equation by a matrix P inverse to make the system easier to solve. As long as P inverse isn't singular, right? The fact that we're even talking about P inverse usually means that it's not singular, because otherwise we would be saying P and P inverse, whatever. The answer doesn't change as a result of this. So there are three types of preconditioning. Left preconditioning, you're literally just multiplying your entire equation by that P inverse. Right preconditioning, which is a bit more complicated. Now the inverse P comes on the other side of the matrix. And you also have to do this two-step solution. And this is like back substitution, right? We would decompose PLU and then solve, right? And all these things are faster. Or you could do two-sided preconditioning. And two-sided preconditioning is very literally the combination of the other two. The two-sided one is useful when you have a symmetry in A. The problem is that if you have a symmetric, so the product of two symmetric matrices is not necessarily symmetric, which is a giant pain, because symmetry is great. You can save half your memory. But in general, multiplying a matrix by it will actually torpedo the symmetry, and you'll be back with an asymmetric thing. So if you want to keep it, generally what you want to do is this double-sided, and typically what you would do is have a, let's see, I think this is an orthogonal matrix, but the idea being that the transpose is equal to the inverse, in which case QAP inverse is symmetric. Great. I think it's called a similarity matrix transformation. I might be wrong on that one though. Okay. So why are we like carrying around this P inverse thing, right? Why don't we just call it P? As we said before, for sparse matrix A, the inverse is not sparse. And this is like, you know, flashbacks, PTSD of that matrix that all of a sudden turned from this nice banded structure to the black box of death, right? Like, we don't want to do that. So instead, what we do is we store P, our ideally sparse preconditioner, and the means by which to calculate the inverse, or more precisely, the action of the inverse, we would say, right? So what that means is like the LU decomposition. We don't store A inverse. We store L and U. We don't even store those inverses. We just store those factors with the knowledge that the substitution step is efficient. Exactly the same idea. Okay. qualities of a good preconditioner as per the assignment number 1. I think almost everybody got that one. The best preconditioner is the matrix itself because A inverse times A makes the identity and the system is therefore solved. In general, we don't have that. So we need P inverse is approximately equal to A inverse in some sense, right? A lot of hand waving going on here. This can be quantified by the condition number of the preconditioned matrix. This is right condition number, right, which we aim to make equal to 1. That's the goal. That's the point. The quality is based on a few things. First of all, speed of computation and application of P inverse. So if P inverse is this super dense thing, then you're down to like dense matrix multiplication, which is slow. Don't want to do that. It also, you can't store it very efficiently. Don't want to do that one. If your preconditioner is the best preconditioner in the world, but it takes the age of the universe to calculate, it's also useless, right? So we don't want that either. In which case, we may actually just use A inverse as your preconditioner. The memory requirements I talked about with regards to sparsity. The degree of additional sparsity from the matrix A. So if you have this nice A banded structure and all of a sudden you have a new matrix that you form from it that has like non-zeros turning into zeros turning into non-zeros, that's termed fill-in. I haven't come across an exact mathematical definition of fill-in. I think they just usually like qualify it as, oh, this is filled in. We want to avoid fill-in. So no need to know about that one. The big money maker is a parallelizability. I need to consult Grammarly on that one. Parallelizability? Parallelability? Anyway. Yeah. Again, I'm going to come back to that one when I talk about HPC. So all this has to be worth it. Previously, with direct methods, we talked about computational complexity. We can't really talk about that anymore. Some preconditioners do have a computational complexity associated with that. Some, if you do it right, actually guarantee convergence of your iterative solver in like a limited number of iterations. But even then, it's too hokey, to be frank, to use a technical term. So a lot of people characterize it instead with regards to the amount of time that it goes. But it's a lot more hit and miss in terms of that characterization. Let's see. The other aspect is actually stability of solving these things. So when we're going to do like nonlinear partial differential equations, time-dependent partial differential equations, what we're going to be ending up doing is solving linear systems over and over and over and over and over again. If you're running this on a big computer and it goes to t time 99%, you're almost there, and then the damn thing crashes, right? Not a good thing. So it might actually be worthwhile suffering a bit more in the time of execution if you get a more stable outcome, right? There are countermeasures. They're called checkpointing, right? If you solve to this time, then you take a snapshot of that and you can always restart it, bring it up. There's all this other stuff, but now you're solving a solution vector, right? It goes on and on and on like that. So just considerations for you to keep in mind. Okay. Let's discuss some common preconditioners and see their effect on particular systems. Jacobi was also in assignment 1. That's the name of the diagonal scaling that I think almost everybody struck on. I mean, you Google what a preconditioner is and you're going to come up with Jacobi. Come on. So the idea is that you're looking at the diagonal elements of your matrix. And then that becomes, so the main diagonal becomes your matrix P. P inverse is just 1 over those diagonal elements. So this is one case where you can actually store P inverse because it maintains the sparsity pattern, 0 fill-in. Good. As an example, pay attention, example. This is I went to some talk by some like commercial guy and he was like, I'm not allowed to talk about any commercially sensitive things. So I'm just going to do this when you should be paying attention. So I just adopted that one. So example, we're going to solve the discrete Poisson equation on the unit square. An actual real life example. Wow. Okay. Do you guys know what the Poisson equation looks like? What it is? Laplacian equals a constant. That's the idea. So Poisson equation shows up all over the place with diffusive phenomena, heat transport, for example. Okay, heat transport shows Laplacian because what ends up happening is that you get the second derivative. Excuse me. You get the you're doing the divergence of a gradient, and divergence of a gradient means that you end up getting like di by di x squared plus di by di y squared is equal to a something, a constant on the other side. Okay. This particular example is on the unit square, and we are setting the boundary condition to be equal to 0 on the periphery of that square. I don't expect you to know this yet. This is going to be coming later when we talk about finite difference method. This is the code that for a given, you know what, let me back up a second. When you're doing finite difference, we know this is on the unit square. What you have to do is discretize your domain. So, and do it over here so hopefully the people online can see. The idea is that you know that this length is 1. This length is 1. And you need to say how much you're going to chop it up. So in this particular example, it's 10. 1, 2, 3, blah, blah, blah. 1, 2, 3, blah, blah, blah. Right? That's the idea behind discretization. This method will discretize it in n elements. And it's going to assign your heat source, excuse me, the Laplacian constant to be Q. It generates it. Feel free to like go through the code if you want. It generates a sparse matrix. Okay, for 10 discretizations along the edge, we can then generate the matrix. And if we look at the matrix plot, we see that it has a nice banded structure. Problem is that this is I mean, it's banded. It's not like a bandwidth. It's not like tridiagonal or petadiagonal or anything like that. So let's try and implement a Jacobi preconditioner, which is super easy. It's literally 1 over the diagonals. Great. This is all uploaded on Avenue to Learn, so feel free to download it and play around with it. What you can see is right off the bat, we can calculate, because we can explicitly write out what the preconditioner matrix is, we can do something like check the condition number, right? So the condition number without the preconditioning is over 1,000, and with the preconditioning is 32. Great. Does this sound familiar? This is assignment 1, right? Now we're going to use, okay, so this is using the GMRES functions that we talked about last class. Guess that was yesterday, right? We've still got a callback that's printing out what the residual is. PR norm is the preconditioned residual norm. That's what the PR is. And what we're going to do is we're going to call it using A, our matrix, F, our vector, without the preconditioner. That's the first line. And then with the preconditioner here in the second line. When we run that, we see this is the residual versus the number of iterations, and they look almost exactly the same. Meh. The difference here, if you look more closely, is the amount of the relative norm that's there. So what's happened here is all we've done is diagonal scaling. We've taken the large elements along that diagonal, and we've just kind of scaled them out. What I tried to do is see actually if there was any difference. Like in practice, one reason why you want to do this is to improve numerical stability. With 8 iterations, there wasn't really enough time for any kind of round off error to accumulate. So even if you look at the difference between the 2 solution vectors, it's effectively nothing. It is 0 in machine precision. All right, and that's why Jacobi is not actually so useful. Incomplete LU. ILU is a much more interesting preconditioner, but it's still hit. I mean, they're all hit and miss. ILU is too, is no exception. For a sparse matrix A, L and U factors are more filled in than the original matrix, which increases memory usage. So instead of, I'll show you guys. You know what, I'll just show you now. So this is the same discrete Poisson. Here I increase to n is 100 discretizations just to make it a bit heftier so we can see some more interesting things. Here is the structure. You can't see the banding anymore, but it's still there. Compare that to the L and U factors, and now you see all this interesting fill-in. The sparsity is very different for L and U than it is for A. And the problem there is that now these things are bigger. They take up more memory. So instead of doing that, we can look for factors L and U such that L and U multiplied together make P, and P is almost A, right? So we're going to almost invert the thing. And the idea is that we're going to take the sparsity of the original matrix and try and only find the elements in L and U that match up to that sparsity. That's called ILU 0, zero fill-in. Alternately, what we can do is match the sparsity of A to a power. And I don't actually know why that's the way to do it. That's one of the mathematical spaces, Lipschitz, whatever, on and on. But that gives you the ILUK family of algorithms. That's what it's going in. Generally speaking, the more dense your preconditioner matrix is, the faster it's going to be able to solve. The less iterations it will take to converge. Not necessarily faster to solve. I love that. That's hilarious. Okay, so we saw what happens to L and U. Let's do sparse ILU and apply it to the system. Do you want me to walk you through the code here? Is that, you guys can just read it along? Okay. I'm going to highlight the big functions here. Discrete Poisson, that's the one that I defined above. SPLU is sparse LU. Hooray! We defined that in the SciPy sparse linalg package. Note there's also SPILU, which we're about to use, and then we plotted that. This is all AI generated. This is from Gemini. All right. Let's find the ILU. What we end up doing is calling this function sparse ILU. We give it A, we give it the fill factor. This is a level, in this case 20. There are other options that you can pass it, like the drop tolerance. The idea there is that you don't need to store elements that are very small. Well, that's a really dangerous thing to do, because usually when you invert things, all of a sudden your small things become large things. So, you know, danger. This is something new. This is, you take the problem here is that, again, you don't want to store the inverse of your preconditioner. So instead, what you want to do is tell the method what happens when you multiply that preconditioner by a vector. This is the kind of hinting towards the matrix-free method. Again, we're not going to go into this anymore. Just remember that certain methods, you'll need to put it into this type of format. So ILU solve is what actually solves for that inversion. It keeps it all inside its memory, the L and U factors, and then it applies them through substitution in an efficient way. Okay, this is all coded into the super LU package. That's what SciPy SPILU calls. All right. Again, we're defining our residual vector. Again, we're calling GMRES. And we're recording that, and we're going to do that twice for unpreconditioned and preconditioned. And for this very particular example problem, the effect is tremendous. We go from 1,200 iterations to find a solution to 10, which is fantastic. Normally, you wouldn't do 20 levels of fill. If you're going to do 20 levels of fill, honestly, you may as well do like LU decomposition at that point. But this is the example that was in that HPC resource that I put in here, and it's like, wow, this is very dramatic. So here's why it's here. All this is working because ILU is cheaper to solve than LU, and it's an approximate answer such that you can put it into GMRES and have it narrow down the answer for you. That's the idea. This is a plot of the solution just to show you guys this is what happens when you solve a Poisson equation that has that form with that source term, that 1, and you see on the boundary is your boundary condition, which in this particular case is 0. By the way, just as a random comment, if instead of 0 you were to lift the entire thing up, so the boundary condition was, say, 100, and because it's a linear system, the effect of increasing that boundary is literally just to lift the entire thing up. So everything in here becomes that plus 100, or whatever the boundary condition is, for example. Okay. Sparse approximate inverse is yet another preconditioner. The idea is that we're attempting to minimize the Frobenius norm, which is just the sum of all the elements squared of this matrix, which is obviously minimized when P is equal to A. You get the inverse, and then you have 0 in there. This is the algorithm. You don't need to know this, to be entirely frank. This is a different matrix. This is not the discrete Poisson equation. This is something else. But again, we can calculate, yes, the condition number does improve. And here the iterations are also very dramatic. So the reason why I wanted to put this in is just to show you there are, like, you have to know the type of equation and your boundary conditions and the boundary conditions, and then you can find an appropriate preconditioner, and the effect can be very nice. I mean, this is huge. That's great. Okay, I'm going to come back to my general advice with that one moving forward. But first of all, preconditioners and high performance computing. The idea with HPCs is that you no longer have a single computer. You now have a million computers. And those million computers are connected on a high-speed network. Each of those computers has at least one core, maybe it has multiple cores, and its own block of memory. As opposed to if you have a single computer with multiple cores, they're all sharing the same memory, right? It's shared memory versus distributed memory. The problem with the distributed memory is now you need to communicate. Those blocks need to communicate with each other, right? And this becomes a bottleneck. And now the whole name of the game is how do you get everything working together? Okay. What we can do though is, well, let's see. So parallelized direct solvers do exist. They're called multifrontal methods. That's actually what LU decomposition is in the modern paradigm, in the modern tools, but they still scale very poorly with the number of nodes. So if you request HPC time and you say, well, I'm going to use UMFPAC or LU decomposition on this, you're going to get your request turned down, to be honest, because at that point, you may as well leave your own computer running longer as opposed to using HPC to get a higher throughput. Iterative solvers do parallelize better, but they need the preconditioner. Since the preconditioner does not have to be a perfect inverse, since we're going to be doing this iteration scheme that does parallelize well, this is where you can use HPC. The idea is that you're going to split up your problem in some sense and have each one of your nodes working on some subset individually, which is fast because it's local, and then they communicate together. That's the general idea. So for the next two examples that I'm going to talk about, I'm going to focus on partial differential equations. And I should also mention that these are, I would say, geometric methods in that you have some awareness of what the geometry that you're looking at is. Okay, let me come back to that one for a second. Typically, a linear solver will see nothing but the matrix, right? If you see nothing but the matrix, you don't necessarily know where it came from. These methods, there are algebraic ways where you don't need to have that geometric awareness. These methods you generally do. Domain decomposition is exactly what it sounds like. You take your geometry, which is a 3D domain, and you literally decompose it into partitions. So you have software. I think Métis or Paramétis is the modern way to partition these things. And what you do is you break it up into different chunks. So this is an example of a finite element method. I literally just pulled it off some guy's paper. I think it does it really well. And what you can see in this diagram is, so all of these triangles is an element that you're going to be solving over. But the colors correspond to your partitioning. So you would have one node that's chewing on the dark blue, another one that's chewing on the green, yellow, and red. What you might be able to see is that there's also a little bit of intermediate colors between here. This is an example of the additive Schwartz method. And the idea is, what are you laughing at? Schwartz? Right? The idea is that you're literally taking your domain, you're breaking it up, and then the question is, how do these chunks communicate with each other? Additive Schwartz overlaps. So you get, not even that funny, whatever. What you end up getting is a region of overlap between these different nodes, and that's how you communicate. And then you iterate on the whole, and that overall iteration smooths out the differences between those two nodes. The nice thing about this is actually what I'm going to recommend as the go-to if your LU fails. The nice thing about this is that each individual node can run its own LU solve. And that's going to be fast because you've partitioned your massive domain that's 1 million DOFs into what, 100 different nodes that are all 10,000. And 10,000, generally speaking, a direct solver is going to be faster than your iterative solvers. So this is good because direct solvers generally work. They're very robust. And then you're leaving it to your iterative method to kind of smooth out and smooth out the differences between those different chunks to stitch them back together. The problem with these guys, so imagine this for a second. Say we're modeling this board, right? And I'm going to partition it something like blah, blah, blah. Okay, something like that. Now I'm going to do something like this over on this side. I'm introducing an elastic wave. But in order for, and that elastic wave travels at the speed of sound in the material very fast. That's why you can normally do it quasi-static. That wave, the information, propagates from here to here because it's all one chunk very fast. But then it needs to propagate through this one, and 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 this one. It's going to reflect off the board, off the other edge, and it's going to go that one, 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 reflect again. It's going to go back and forth. So if you have the type of physics like quasi-static elasticity, this is gonna, you're gonna be paying for this. It's not gonna want to converge because that information is being passed along so fast. Enter multigrid. Multigrid is the modern go-to if it works, and it's kind of hard to get working. The idea is actually really cool. This is another geometric one. You need to have the information about what the geometry is, at least for geometric multigrid. There's also algebraic multigrid, which I have never in my experience actually gotten working for anything more than like the demo problem that's included with the software. But the idea is you take your actual problem, which is your fine resolution. We talked about discretization. And you generate a hierarchy of meshes. So if you want 100 by 100, you start off with 5 by 5. And then you subdivide those. And now you have 10 by 10. Now you have 20 by 20. Now you have 40 by 40. Now you have 80 by 80. Now you have more than 100, 160 by 160. And the idea is that you can solve that on your coarse grid, which is small. So you chuck that as an LU solve, very robust, it gets an answer, and then it propagates that information. And it takes that and it interpolates it down and iterates on it a little bit. Usually Gauss-Seidel, actually. I did say that Gauss-Seidel actually does pop up, or SOR, the generalization. That's where it happens. It iterates only like once or twice, which is fast, propagates it down, chews on it a little bit more, propagates it down, chews on it a little bit more. And then there are all sorts of different patterns. They're called V cycle, F cycle, W cycle, right? That kind of goes up and down between these scales. The nice thing about this is you don't need overlap in this case. What happens is the communication between those blocks is accomplished by the layer above it. And that becomes very efficient. Mathematically, the full analysis actually shows that it's basically what you're doing is kind of almost Fourier decomposition. So this is, again, this is like a little bit of a decomposition idea. Each grid, each layer reduces the frequency. So let me back up. You have your residual, your problem residual on each layer, right? Consider that residual as a signal with different Fourier frequencies embedded in it. Each one of those layers, that discretization, will optimally damp one of those signals, one of those waves. So the very fine grid is going to really hit the super fine frequencies in your residual. The super coarse one is going to really hit the really wide, the really long scale waves. So for elasticity, very, very useful for elasticity. Just mind-blowingly how good this thing is at elasticity. This, when I'm doing this, that wave is immediately transferred over there. And then it's set. And unless I'm doing like another harmonic or something, my problem is basically done at that point. It's super, super efficient. It's actually considered ideal scaling. So if multi-grid works for you, that's what you want. Where did I have it? Yeah, you can actually achieve order n scaling with the number of nodes. So if you want like the big machines, that's what you're going to be going for. Unfortunately, it's not as robust. Like it's still not as robust as LU solves. I'm going to pick it up here because I wanted to touch on the assignment too. Okay, multiphysics. You guys have all done computational multiphysics. Did you actually couple different types of physics? Okay. When you do that, I guess all this layer was hidden for you, right? When you do that, different types of physics, I've already spoken about like how elasticity works very well with multigrid. Heat transport, the Laplacian, the Poisson's equation that we just did, responds well to ILU, right? Wouldn't it be nice if we can target that preconditioner for that type of physics and then bring it together so we can do something like heat transport with elasticity coupled? Turns out that you can at least propose the problem, in which case it looks like this. It ends up being a block matrix system. At least block matrices are actually kind of intuitive the way they work. What you're going to get is degrees of freedom for your temperature field, and in this case, your concentration field. This is coupled mass heat transport. So you're going to get your unknown vector for temperature, your unknown vector for concentration. You actually are going to get a separation of your system matrix, your A matrix, belonging to A PT. That's your temperature. That's your Fourier temperature heat transport. You're going to get another one for your Fickian diffusion. And then you're going to get these cross terms. And the cross terms do things like temperature-dependent diffusivity. Diffusivity, activation energy, you're looking at Arrhenius, so you have a temperature dependence, right? Similarly, you might have concentration-dependent thermal conductivity. That's what these cross terms are. And then you have whatever you need in your constant vector. Looking at it this way is sometimes called operator split methods. Physics-based preconditioners, if anybody is going to be using MOOS, the finite element package out of the US, Idaho National Labs does MOOS. It has various animals in the herd. Bison is a big one. You guys might hear about that for graduate studies. They like using the term physics-based preconditioners. This is what they're talking about. Segregated solvers. If you end up using COMSOL multiphysics, they call this a segregated solve. Different names. It's all talking about the same thing. Field split method is what PETSI does. Okay. How do we effectively precondition? Joke's on you. We don't. That's my opinion. One thing we can do is called the Bloch-Jacobi matrix, the Bloch-Jacobi method. And what we do is we take our preconditioner to be, again, the diagonal elements. And if you remember, I think it was lecture 3, the inverse of a block diagonal is also block diagonal. So whereas the goal is not to fill in these nice zeros in the block sense, we can still do this, which is kind of nice. My experience, block Jacobi is about as effective as regular Jacobi preconditioning. What is nice is something called block-Schur complement. This is actually Gaussian elimination applied to a block matrix, is where it comes from. Basically, the idea is that the inverse of a block matrix can actually be decomposed into the various indices of those blocks, the inverses of those blocks. The thing that is going to sink you here is that you have I shouldn't have named it this. This is just the standard way to do this. This A inverse, where this A is referring to the block, not the total thing. Because you have an inverse thing, right? You've spoiled your sparsity. And remember, the sparsity is really what's going to be saving you in these things. So that's kind of the problem. So you don't actually solve the analytic A inverse. What you end up doing is storing an approximation of the inverse, and that kind of spoils the rest of it, to be entirely honest. Again, in my experience, with the exception if, for example, C or B are 0. Because if one of these guys is 0, this funny business term here becomes 0, and then you're off to the races. But there are also some good applications of this sort of thing with optimization, with Lagrange method of Lagrange undetermined Lagrange constants, multipliers. Okay. So what the hell are you supposed to do? Right? I've told you a bunch of stuff that you can do and said that most of it doesn't work. So here's my personal advice. First of all, parallelized LU decomposition is your go-to. It's going to work. It's going to take a long time, and the bigger your system, the longer it's going to take, but it is the most robust. Failing that, GMRES is the next default, right? GMRES will solve symmetric positive definite. It might even be smart enough to be able to use that, right? If you know that your system is symmetric positive definite and you can apply a good preconditioner to keep that property, right? Then you might be able to get away with conjugate gradient, but otherwise, for everything else, there's GMRES. That does need preconditioner. If you're studying a well-known model, then you might be able to just Google it, and some guy will have written a paper. There are actually preconditioners that are well known for example, for Navier-Stokes. Incompressible Navier-Stokes, you have to have your pressure as a separate variable, and there are preconditioners specifically designed for that, which is good if it works. Don't forget your boundary conditions. Your boundary conditions also have to matter for that. If not, most PDE solvers nowadays have the option to mix and match and kind of play with different preconditioners. COMSOL will allow you to do this. PETSI is the portable extensible toolkit for scientific computing. This is what like the supercomputers in the US basically categorically use. MOOS relies on that. The finite element code that I use called Phoenix or Fire Drake relies on PETSI. It considers itself a hierarchical preconditioner building set, with the idea being that you can tell it to apply such and such a preconditioner in such and such a case. So you can do the sure complement for the preconditioner and do ILU for this, ILU 7 for this one, do a geometric multigrid on the whole thing, and you can kind of mix and match. It's really nice because then you can try things. You can try success there. What I have had success for a long time was doing additive Schwartz with LU on the subnodes. By far, that's been the most robust, like failing LU on the monolithic system without breaking it up. Using additive Schwartz, you say with 1 degree of overlap, you say LU on each of the subnodes. That's been giving me the best answers. Aim for about 10,000 degrees of freedom per node. That's your goal. If you have like a number of nodes that you're able to use, that's the threshold. That was a fellow who worked for Petsy, who's writing the Petsy code. That was his rule of thumb. That's the threshold past which it's worthwhile doing it locally versus your communication overhead. Okay. Geometric multigrid is finicky, but when it works, it's like a rocket ship when you're used to a bicycle. Like it just goes. It's fantastic, but it's finicky. Any questions? Now 4 minutes, and I want to quickly go through the assignment here.